This brings us to the first exercise for Module 2. In this exercise, you are asked to use the interpolation macro to fill out the yellow cells in the following tables. For 2.1a, you are asked to calculate y for the given values of x using the specified interpolation routines. So we're going to do the same thing 3 times, but with different transformations: linear, logarithmic, and z-variate. For 2.1b, you are asked to interpolate from the table above for the given xy pairs using a log transformation for both x and y, and linear for z. The first column in the exercise asks us to do a straight linear interpolation. To do this, the function we need is linint. The first input for the function is our x value of interest, which is the 1.26 in cell E10. Next, we input the x array shown in the red box, cells B8 through B12, followed by the y array, cells C8 through C12, shown in the purple box. Because the data is in ascending order, we will input a 1 for the order, which is our next input. And for the last input, we will input 0 to disallow extrapolation. Dollar signs were used to lock the rows and columns of the x and y arrays. This will allow us to drag the formula down to populate the next 2 rows without those arrays changing. So the only thing changing in the formula is the x value of interest. After dragging the formula down, here are the results for the first column. For the second and third columns, the transformation for the y value changes, but that's it. This means that we need to use different functions, but the inputs into the function will be the same as those for the first function that we just showed for linear interpolation. In the second column, we are asked to do a logarithmic transformation for the y variable. The function we need now becomes linlogint, linear or lin for x, and logarithmic or log for y. The inputs for the function are exactly the same as what we used for the first part. The first input is the x value of interest, followed by the x array, then the y array, a 1 for the order, and a 0 to disallow extrapolation. Lock the rows and columns using dollar signs for the x array and the y array like we did before, and we're all set. Drag the formula down and you get the values shown here for y. For the last column, we are asked to do a z-variate transformation for y. The inputs will all be the same again, but the function will change to linzint, linear or lin for x, and z-variate or z for y. Here's the function linzint. Input the x value, the x array, the y array, 1 for the order, and 0 to disallow extrapolation. Add your dollar signs to lock the rows and columns for the x and y arrays. Next, we drag the formula down to populate the rest of the table, and the completed table should look like this. For the second part of the exercise, the z value is a function of 2 variables, variables x and y. We are asked to interpolate to find z for the given xy pairs. We are also asked to do a log transformation for both x and y when we interpolate. The 2D interpolation function needed will be by, log, log, lin, int. Log for x, log for y, and linear for z. The first input will be the x value from cell B29. The second input will be the y value from C29, followed by the x array, the y array, and the z array. The x array is the purple shaded cells that range from B18 to B22. The y array is the green cells from C17 across through F17. And the z array extends from C18 to F22 in the fuchsia box. Dollar signs were added to lock the rows and columns for the arrays because the arrays do not change, only the x's and y's for which we are interpolating. To finish out the inputs, we need the x order, the y order, and then x extrapolation and y extrapolation. Both the x and y arrays are in ascending order, so the inputs will be 1s for both. The instructions tell us not to allow extrapolation, so the next 2 inputs will both be 0. Drag the formula down to complete the table, and that completes the exercise. But before moving on, let's go back to exercise 2.1a for a second. We completed the interpolation 3 different ways using 3 different transformations for y. But which method is most appropriate? If we plot the results, plot some trend lines, and look at the computed R-square values, we can see that the z-variate transformation results in something closest to a straight line and would therefore be the best choice in this instance.